In this video, we're going to discuss specific heat. Now, specific heat is the amount of energy it takes to raise the temperature of 1 gram of any material 1 degrees C. And we're going to look at parts A and B of problem number 155 on page 37. And even though this is chapter 1, we're talking about energy concerns during this module. So even though this was discussed in chapter 1, pardon me, even though this was discussed in chapter 1, we're going to review this and talk about it during this chapter as well, and you might see a problem in your homework on this. Now the formula for specific heat Q equals C times M times delta T. Q is the amount of energy. C is specific heat. M is mass of the material. And delta T is T final minus T initial. Now I remember it this way, country music television, even though I'm not a country music fan, it's pretty easy to remember the formula if you think about Q equals country music television. All right, so this is the formula we're going to use. Let's look at this problem. 155, using table 1.6, calculating calories, the amount of heat that must be added to warm 13.4 grams of each of the following substances from 29C to 51C. All right, and then it asks which substance requires the greatest input of heat energy and why. Well, if we're using the same amount of mass of each of these, it would just depend on the specific heats. I'm not going to do all three problems here. Let me scroll down a little bit, all three parts of the problem, but we're going to just work through the problems just so you are familiar with how to do them and you can get through the homework a lot easier. Well, since all of the three parts have the same delta T, the same temperature concerns, let's figure out delta T first. All right, so delta T, as I said, is T final minus T initial. We're told that the final temperature is going to be 51 Celsius. And the original temperature, the starting temperature, the initial temperature is going to be 29 C. All right, we do this math and we're going to get 22 degrees C delta T. Okay, so that's what we're going to plug in for delta T in each of these formulas. Now the mass is going to be consistently 13.4 grams. The only thing that's changing is the specific heat. So part A, we're talking about water, H2O. If we look at table 1.6, the specific heat of water is 1.00 calories per gram per degree C. Okay, and actually the calorie is defined by water's specific heat. That's why it's 1.00. All right, so let's scroll down a little bit. Get a little room to do this calculation. Q equals C times M times delta T. C in this case is 1.00 calories per gram per degree C. Mass 13.4 grams. And as we said, our delta T is 22 degrees C. Let's take a look at these units. Grams cancel, centigrades cancel, and we're left with calories, and that's great because this needs to be an amount of energy. All right. So we do this math, 1.00 times 13.4 times 22C. We'll get 294.8 on our calculators, calories. And we're looking at, all right, well, let's see, 2 sig figs here, 3 sig figs there, 3 sig figs. Well, this is actually infinite number sig figs because it is a not a measured number, it's an exact number. So we're limited, this is multiplication, we're limited by the 22, we need it in 2 sig figs, so this is going to be approximately 290 calories. 290 calories. So that's part A. Part B is for copper. Copper, the C for copper, is from table 1.6, 0.093 calories per gram per degree C. 0.093 calories per gram per degree C. So let's plug and chug, as mathematics people would say. Okay, C 0.093 calories per gram per degree C. And remember, we have 13.4 grams, and we're raising this temperature 22 degrees C. As before, this is multiplication. What's on top and what's on the bottom will cancel. And we do this math, and our calculator should spit out 27.4164. We are again limited to 2 sig figs here, so we're looking at about 27 calories. All right, and if you did the same thing for sand, you would just plug in from table 1.6 sand specific heat and get a value there. The second part of this question is what substance requires the greatest input of heat, energy, and why? Well, since they're all the same mass, they're all the same temperature change, it's all going to be based upon the specific heat. Which one has the greater specific heat? And that's a question I'll leave for you.